Today, let's explore the concept of numerical integration methods. These are the tools that let us approximate the area under the curve when formulas get tough or when data is all we have. So, why do we need numerical integration methods? Sometimes finding the integral of a function analytically is impossible or too complicated. In real life, measurements come as data points, not equations. By the end, you'll know several key techniques and when to use each armed with real examples. So basically, we are going to look into three types of numerical integration methods today. The first one is the midpoint rule, the second one is the trapezoidal rule, and the third one is the Simpson's rule. First, let's brush up a few fundamental concepts. Suppose you want an integral of f of x from a to b. So this kind of an integral gives the area under f of x from a to b. So how do we do this? So we basically integrate the function and then um, subtract the higher limit minus the lower limit. Now, let us look into the fundamentals of Riemann sums, the bedrock of numerical methods. So, in this method, we divide the interval a, b into n subintervals. For example, if we have 0, comma 2, we divide this and we want four subintervals. We divide this 2 minus 0 by 4, which gives us 0.5 each. So these are the subintervals we're going to turn our main interval into. And summing up the heights of f of x at these specific points times h gives us an approximation. In easier words, at these subintervals, we find the value of f of x, and then we multiply it with h, and the summation of all these points gives us an approximation of what the integral value is. So we can either compute the left Riemann sum, which is the area under the curve, is equal to h into I is equal to 0 to n minus 1. Summation from I is equal to 0 to I is equal to n minus 1 of f of x of I. This is the left Riemann sum. So let us look at an example. First, suppose let's take f of x is equals to x, a is equals to 0, b is equals to 2, and n is equals to 2 intervals. Then h will be b minus a by 2, which will be 1. So our intervals are x0 is equals to 0, x1 is equals to 1, x2 is equals to 2. So according to left Riemann sum, the value of area is approximately equal to h into I is from summation of I is equals summation from I is equals to 0 to I is equals to n minus 1 of f of x, which will be equal to 1 into f of 0 plus f of 1, which is equal to 1. But the actual area of f of x equal to x from the range 0 to 2 will be a b of f of x is equals to 0 to bx squared by 2, which will be equal to 2. So the real area is 2, but the approximation which we got is 1. So this method is not very accurate. In the same way, for right Riemann sum, we use f of x of I plus 1 instead of x of I. So if in this example, we will integrate this h of I is equals to 0 to n minus 1 will become f of x of I plus 1, which will be h of, here h is equal to 1. So we can just compute the value as it is 1 into f of 1 plus f of 2, which will be equal to 2. So the right side approximation of Riemann sum is equal to the real value. You can see this method is not so reliable. So, and the accuracy of this method increases with the increase in the number of intervals. So let us look into better methods. Let's look at the midpoint rule. This uses the midpoint of each interval. For example, just like Riemann sum, we divide our main interval AB into subintervals based on the number of the n we get. Now, what midpoint rule does is it calculates a midpoint between each subinterval and finds the area of this section, this rectangle, and sums all these such rectangles and from A to B to get our approximation of the value of f of x. So let us look into this with an example. The formula for midpoint rule is for f of x dx from limits a to b, the approximate value is equal to h into summation of f of xi star from I is equals to 1 to n. Here xi star will be equal to x of I minus 1 plus x of I by 2. And h will be b minus a by n. So first suppose we have to approximate this function on n is equals to 2. So how can we do this? First, let's calculate h will be equal to 1. And the midpoints, so the intervals we get is x of 0 is equals to 0, x of 1 is equals to 1, x of 2 is equals to 2. So the midpoints from 1 to n, that is x of 1 to x of n, which is x of 2, will be m of 1 equals to x of 0 plus x of 1 by 2, which will be equal to 0.5. Similarly, m2 will be equal to 2 plus 1 by 2, which will be equal to 1.5. So if we want to find the value of f of m1, where f of x is equals to x square, this will be equal to 0.5 square, which will be equal to 0.25. And f of m2 will be equal to 1.5 square, which will be equal to 2.25. Now, according to midpoints theorem, the area will be approximately equal to h into summation of this I is equals to 1 to n, which is equals to 2 of f of xi star, which is xi star is none other than our m terms. So this is equal to 1, summation of I is equals to 1 to 2, or we can write this as or we can write this as 1 into f of m1 plus f of m2, which will be equal to 2.5. So this is the value which we got from this approximation. So the real value of this function from the interval 0 to 2 will be x power of 3 by 3, 0 to 2, which will be equal to 2.6666. So we got a very close approximate of the real value. So the pros of midpoint theorem is that it is more accurate than the left or right Riemann sums for the same n. And to make this approximation better, the more the intervals we use, the better result we get. Now, the error rate of this midpoint theorem decreases at the rate of 1 by n squared. That is, the error decreases in the same way how the curve 1 by n squared does. So the as we increase the number of intervals, the error decreases significantly. Now let's look into the trapezoidal rule. So in trapezoidal rule, instead of triangles, we use trapezoids, which hug the function better. That means which you know make better approximations by fitting straight lines and making trapezoids with each subinterval. So the formula for the trapezoidal approximation is for f of x integral d of f of x d of x over a to b. We can say that it is approximately equal to half of the h or the size of the interval into f of x naught plus 2 into f of x1 plus 2 into f of x2 so on till 2 into f of x n minus 1 plus f of xn. So we can write this as simply half of the interval plus f of x naught plus 2 into summation of I is equals to 1 to n minus 1 of f of x of I plus f of xn. So in simplified terms, this is the formula for trapezoidal. Now, if you look at the same example where f of x is equals to x square, and we want to integrate it over 0 to 2, f of x dx, and n is equals to 2, and h is equals to 1, we can find the approximation by plugging the values of f, the function of x naught, x1, and x2 into this equation. So, according to this equation, our approximate value or area will be h by 2 of f of x naught plus 2 into f of x1 plus f of xn. This will be equal to 1 by 2 of x naught, which here x naught is equals to 0, x1 is equals to 1, x2 is equals to 2. So 1 by 2 of f of x naught will be 0 square, which is equal to 0, and 2 into 1 square is equal to 1, and 2 into 2 square. I'm sorry, is equal and 2 square. So we can write this as 1 by 2 of 6, which is equal to 3. But the actual value of the function is equal to 2 point. This is equal to 2.666. So the value which we got using the trapezoidal rule is 3, which has a large range of error. Because trapezoidal approximation works well with linear functions. So there will be some overshoot with functions like this. Now, the pros of trapezoidal rule is that they generally move more accurately than midpoint, other than some cases like this. And the error is proportional to 1 by n squared, just like the midpoint theorem. Now, let's look at Simpson's rule. Unlike midpoint rule and trapezoidal rule, Simpson's rule uses parabolic arcs rather than lines or flat rectangles. And the other main thing which we have to focus is that n should always be even, because this function works best when n is even. Okay. So the formula for Simpson's rule is for integral of f of x dx around a to b is approximately equal to h by 3. That means the size of the interval by 3 whole into f of x naught plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus 2 times f of x4, so on till f of xn. So basically, the function is something like this. In f of xi, if I is odd, we multiply this with 4. And if I is even, we multiply this with 2. So generalizing this, we can write it as h by 3 f naught plus odd of 4 into y plus 2 into even of xi plus. Just like the trapezoidal rule, this inner part, this inner part only grows from 1 to n minus 1. We just add f of x, f of x0 and f of xn without multiplying them with any constants. So let's look at the same example in Simpson's rule, where f of x is equals to x squared, and we have to find 0 to 2 f of x dx, and n is equals to 2 and h is equals to 1. So this equation will become approximately equal to 1 by 3 into f of 0 plus 4 into f of 1 plus f of 2, which will be equal to 1 by 3 into 0 plus 4 plus 4, which will be equal to 1 by 3 into 8, which is equal to 2.66. So this gave us a more approximate or more closer value of the function compared to trapezoidal and midpoint theorem. So the pros of Simpson's rule is that it has great accuracy. The error is also proportional to 1 by n to the power of 4. So the error decreases as rapidly as the function f of x is equals to 1 by n to the power of 4 decreases. So small increases in the number of intervals can give us a better approximation using this rule. Now that we understood the working of all three numerical integration methods, let's take a look at a small comparison between them. If you can see, the midpoint rule gives a good accuracy and the complexity is very simple. It is best used when we need quick estimates and we have smooth curves. And if you look at the trapezoidal rules, sometimes it might be worse than midpoint, but mostly it outperforms midpoint and it is better than midpoint. And the complexity is not as simple as midpoint, but it's simple. It works well for linearish functions, as we discussed, and more points. And more points in the sense, more data points. And Simpson's rule is the best because the error in this rule converges as fast as the function 1 by n to the power of 4 converges. So with small increments in the intervals, we can get better approximations of the function we need. The complexity of calculating the approximations using this function is moderate. And this function works best for smooth curvature functions and even n, that is even number of intervals. So this is about numerical integration methods. So to summarize all the methods which we discussed today, we can say that each of these methods have their own strengths. But collectively speaking, the more intervals you use in these methods, the more better approximations we get because of their error and proportionality with 1 by n square and 1 by n to the power of 4. Now, to choose the best method, we need to focus on the function shape which we are giving to the method, the need for speed versus precision. Thank you.